For decades, quantum computers were pure science fiction. Machines that could crack any code or simulate entire universes in an instant. Today, that dream is inching closer to reality. In labs around the world, intricate machines of metal, wires, and extreme cooling systems are taking shape. These early quantum computers are fragile and limited, but they mark a monumental leap from theory to practice. The journey has demanded a deep dive into the bizarre quantum world, where particles can exist in multiple places at once and be linked across vast distances. Building a machine based on these principles once seemed impossible, but relentless scientific effort has made the first prototypes real. Now, the big question, are these early quantum computers the dawn of a new era or just expensive curiosities? In this video, we'll explore how quantum computers work, the progress made, and the challenges ahead. Let's dive into the quantum realm and see what the future might hold. Classical computers use bits, ones and zeros, to process information. It's a system that's powered the digital revolution. Quantum computers, however, use qubits, which can be both 0 and 1 at the same time thanks to superposition. Picture a spinning coin. While in the air, it's both heads and tails. Only when it lands do we see a definite result. Qubits work the same way. This means quantum computers can process vast combinations of information simultaneously, growing exponentially with each added qubit. With just 300 qubits, a quantum computer could represent more values than atoms in the universe. But there's more: entanglement. When qubits are entangled, their states are linked, no matter the distance. Change one and the other responds instantly, what Einstein called spooky action at a distance. This allows quantum computers to coordinate calculations in ways classical computers can't. Superposition and entanglement together create the quantum leap in computing power. That's what sets quantum computers apart. Quantum computers promise to tackle problems that stump even our best supercomputers. In cryptography, they could break codes that protect our data, using algorithms like Shor's to factor large numbers in seconds. In medicine and material science, quantum machines could simulate molecules with unmatched accuracy, speeding up drug discovery and the creation of new materials. Finance could benefit from quantum models that optimize investments and manage risk in ways classical computers can't. Quantum AI could revolutionize pattern recognition and logistics, solving problems like global shipping routes with unprecedented efficiency. Scientists could use quantum computers to simulate black holes, explore the early universe, and probe the nature of reality itself. The potential is transformative, opening new frontiers in science, industry, and beyond. The possibilities are just beginning to unfold. Quantum computing is no longer just theory, it's happening now. In 2019, Google's Sycamore processor achieved quantum supremacy, solving a problem in 200 seconds that would take classical supercomputers thousands of years. While the task was highly specialized and its practical value debated, it marked a turning point. IBM has pushed forward too, building chips with hundreds, and now over 1,000 qubits, and making quantum computers accessible via the cloud. But today's machines are noisy, error-prone, and require extreme cooling, just a fraction of a degree above absolute zero. These quantum processors are engineering marvels, but they're massive, expensive, and need constant expert care. We have working quantum computers, but they're far from everyday devices. The technology is real, but still in its infancy. The race is on to make them practical. Building a large-scale quantum computer is one of science's toughest challenges. Qubits are powerful but incredibly fragile, easily disturbed by their environment, a problem called decoherence. Even tiny vibrations or temperature changes can destroy quantum information in microseconds. That's why quantum computers need extreme isolation and cooling. Error correction is another hurdle. To make one reliable, logical qubit, you might need thousands of physical qubits. Today's machines have hundreds or a few thousand noisy qubits, nowhere near enough for full error correction. Overcoming decoherence and error correction demands breakthroughs in physics, engineering, and materials science. The path is steep, but every small advance brings us closer. The quest continues. Quantum computers are in a league of their own when it comes to cost and complexity. Unlike mass-produced laptops or even supercomputers, a single quantum computer can cost tens of millions of dollars. Most of that goes to the specialized cooling systems, dilution refrigerators, and the custom electronics needed to control and read out each qubit. Every qubit adds to the expense, requiring precise microwave controls and sensitive amplifiers. On top of the hardware, you need teams of highly trained experts to build, operate, and maintain these machines. That's why quantum computers are currently found only in major corporations, government labs, and elite universities. For now, quantum computing is a high-stakes, high-cost endeavor. When will we have truly powerful quantum computers? No one knows for sure. Some optimists predict breakthroughs within a decade, while others say it could take 20 to 30 years, or longer. The main obstacles: building stable qubits and achieving reliable error correction at scale. The future may not be a single all-purpose quantum computer, but a hybrid model, quantum processors working alongside classical supercomputers. Progress depends on scientific discovery and engineering innovation. The journey is a marathon, not a sprint, requiring patience and collaboration across disciplines. The quantum revolution is coming, but its timeline is still uncertain. We're living in the NISQ era, noisy intermediate-scale quantum. Today's machines have 50 to a few hundred qubits, enough to surpass laptops, but not yet ready for the biggest challenges. Noisy means these qubits are error-prone, limiting the complexity of calculations. Researchers are developing hybrid algorithms that split problems between quantum and classical computers, making the most of current hardware. This era is about learning, testing theories, developing new algorithms, and gaining hands-on experience. Companies in chemistry, finance, and logistics are already experimenting with cloud-based quantum systems. While we're not solving billion-dollar problems yet, we're building the expertise needed for the future. The NISQ era is a crucial bridge between today's limitations and tomorrow's breakthroughs. Every experiment brings us closer to practical quantum computing. The groundwork for the future is being laid right now. We stand at a crossroads. Quantum computers are no longer just dreams, but real machines humming in labs worldwide. Their power comes from the strange rules of quantum mechanics, offering a fundamentally new way to process information. The challenges are immense: decoherence, error correction, and cost. But progress is undeniable. The NISQ era is paving the way for breakthroughs in medicine, materials, AI, and our understanding of the universe. Quantum technology could reshape our world in ways we can barely imagine. The future isn't guaranteed, but it's a possibility we're building, one qubit at a time. Which quantum possibility excites you most? The revolution is coming, shaped by the problems we choose to solve and the dreams we dare to pursue.